by formulating the Van Kampen's theorem. So let me remind you the conditions and the setup. We have X covered by open subsets A alpha, which so they all contain common point x0, which will be our base point. Then for each of these A alphas, we can consider canonical inclusion map into X. So inclusion maps intersections to one of them, right? Here the order of indices is important. And, by our assumptions, individual sets and all pairwise intersections are path connected. Then we want to, by corresponding J, J alpha will denote the corresponding push forward of I alpha, which will be mapped from pi1 alpha. Base point will be everywhere x0. X, corresponding to J alpha beta. So this is a push forward alpha, and this will be a push forward beta. Pi1, yeah, alpha beta. Alpha. Okay, and then theorem. Can be split into two parts. First part is that if you consider phi to be a map, which is a free product homomorphisms J alpha, so this will be by definition of the free product of homomorphisms, this will be a map from free product pi1 of alpha A alphas X. Here again, the base point is everywhere x0. The statement that this is surjective. Any element in pi1 can be obtained as a as an element of free product pi1 of pi1s of all individual subsets. And the second part assumes assuming that over all triple intersections are path connected. And then we have explicit description of the kernel of this map. Kernel phi so this is a subgroup here, and it's the statement is generated by elements following form. G alpha beta of omega times J beta alpha of omega inverse, where omega runs over all possible elements of Y1 intersection. This is this means a group generated by these guys, where omega runs over elements of pi1 of intersection. Because from intersection we have a pair of map. You can consider a map from I alpha b, J alpha beta, and yeah, so since J alpha beta maps you to pi1 of A alpha, and J beta alpha maps you to pi1 of A beta, and both of them, they of course subgroups in the free product, right? Just consider the word. So there is of course a canonical inclusion of pi1 alpha 0 into product. By considering here, for example, you consider word of a single with a single element just being element here.
Sorry, what is n in the kernel of f? No, omega, this free word belongs to what? What is that n in front of that intersection, alpha beta? What kernel?
Where is it? Where is it here?
Inside. Free word omega belongs to something.
You don't see what is here?
No, omega, which set? Which of set? Omega set. Which of
Omega is in this is an element of pi1 of A alpha.
pi1 there. Okay.
Yes. Well, which yeah. And this is, well, if you wish, so this is element of pi1 alpha, and this is element pi1. This is just by definition of how your J alpha beta acts. So if you want to understand this as a kind of word with two symbols, one symbol is element of this group, and the other element is of this group. So it defines a particular element.
Just I confuse that word. Words just writing. I confuse it. Thank you.
In particular, automatically from this statement, since we have an explicit description of the kernel of this homomorphism, we know that this is a map surjective by the first part. This tells us that in the image of the homomorphism is anamorphic to the quotient of the group where homomorphism acts from over the kernel. We get that pi1 of x0 is isomorphic to pi1. Sorry, the quotient of the free product by this kernel. So let me denote this subgroup just by n. So this will be just definition of n as a subgroup. So n is a subgroup here defined as follows. So defined by these generators. And yeah, the statement which you want to prove is that the kernel is equal to this subgroup n. What is formulated. So any other questions about the formulation of the theorem? Well, let us then start with the proof. So the first part, it just follows from the lemma that you showed. Right? Because lemma, we showed that any loop, any loop represents an element in pi1 can be represented as a composition of loops, all individuals A alpha. Means any element in pi1 can be obtained by this map. So essentially, we only need to show the second part. And well, this will require some work. Again, we will need some sort of analysis to do this. So it is useful to introduce kind of the following terminology first. So let us call formal product a formal product word calling form. So the formal product of elements like this, where each fi in a bracket is an element of pi1 alpha. So far we don't say anything about this being reduced or not. So it's just a formal product or a word, just a sequence of such element. And of course, fi representing such element is a loop set A alpha. So we call such formal product a factorization the definition of what factorization is. A factorization of an element bracket of f pi1 of x, our total space. In f here is a loop in x. If, by definition, f is the path homotopic to the corresponding composition of loops fi. Again, from the lemma, it follows that it's always factorization for any element of pi1. Factorization always exists. And now we want to consider the following equivalence relation on factorization. First, so if you have a first pair of equivalence is actually the same as equivalence relation, which you use to define the free product of groups. So it will be that if I have some element in the middle of my factorization, which is just identity pi1 for the corresponding A alpha I. So let me. I was A alpha I is a subset where our small loop fi lives. So we can. This is equivalent just by with this element removed. And if you have a pair subsequent elements which are both belong to pi1, so some common pi1 of alpha for some alpha, we can replace this pair to a single element, which is a class of, sorry, here in my notation should be minus. Yeah, the point is that there are a sequence of two consecutive elements. We can replace it to a single guy just by considering a class of the composition. In other words, you just use a product, group product pi1 of A alpha. So this essentially tells us that if you include this equivalence relation, that this defines a particular element in the free product of pi1 of A alphas. And we also want to consider another equivalence relation. We have somewhere in our formal product element fi belongs into some pi1 of A alpha for some alpha. But we also know that suppose that this loop fi, so we know that, so we already know that this is a loop in alpha. So its image of the corresponding map is contained in alpha. But suppose it's also belongs to some A beta. So it's a loop contained in both A alpha and A beta. And then we, what we want to do is say that this factorization is equivalent to factorization where we kind of have the same thing, but now this element here is treated as an element of pi1 A beta. And the notation is the same, but this is considered as an element of pi1 of alpha, and this is considered as an element of pi1 of A beta. And one can rewrite it. One can rewrite this relation as follows. So since the the image of Fi is contained both, is contained, for example, both in alpha and A beta. This means that it contains in the intersection, right? So one can also consider Fi, this class of Fi, one can also consider as an element of pi1 of the intersection. Let us denote this to be omega. Again, consider it as element of pi1 of the intersection. And then on the left, we can write it as a this Fi as an element of pi1 of alpha as an image of this omega under the push forward, which we denoted J alpha beta, right, of omega. And this is same as push forward J beta alpha of omega. Just by definition of this forwards of inclusion, right? And we can also write this J alpha beta of omega just tautologically as G alpha beta of omega times J beta alpha of omega inverse. This whole thing times J beta alpha of omega, which is the same thing as we have here. And this, by definition of our group, subgroup N, this is N. This is an element of N, just by definition of N. N we just define as a subgroup generated by element of such form. And we want to show that this N is a kernel of our map phi. But what we already see by construction of our equivalence relation, this just follows by definition of our equivalence relation on factorizations, is that equivalent relations, sorry, the equivalent factorization relations give the same element. Quotient, the quotient of free product of pi1 of A alphas by N. This is just first we show that the equivalence class of factorization defines gives us well-defined element of pi1 because it respects these equivalence relations which are used to define the free product, and moreover, the second part of the equivalence tells us exactly that the elements of we want to consider elements of the free product to be the same, meaning to be equivalent if they differ by an element of N. And we also essentially our task is to show that the converse is also true. That well, essentially any, so this is you don't get anything else, in the sense that that any, I want to show any two factorizations are equivalent. Meaning that if I choose any other factorization, meaning that there will be a sequence of FIs such that their product, sequence of classes of FIs as a product such that the composition of these FIs, the kind of small loops living in alphas, is path homotopy to F. If I take any other sequence like this, it will be necessarily the corresponding formal product will be necessarily related to it to our original factorization by a sequence of such relations as we have here. Particularly, this will show that there is a bijection between phi1 of x and this quotient. And in other words, will show that if you consider a map phi tilde from the quotient, the product divided by n, to phi1 x, just by if you want, you can write that this is so you take a word here, and you consider its class under this equivalence relation which we defined, and you send it to F, for which furnishes a factorization, then this will be injective. So it is obvious that this map is well defined because yeah, the equivalent factorization, they definitely give you the same element, the same element in pi1. Under all these changes, the composition of the corresponding path is the same path. All these relations, they which we have here, they preserve composition itself, right? Just kind of you can see the different parts, treat different parts in a different way. And since this is injective, this means that the kernel of the original map phi, which was just a map from free product to pi1, was exactly n. So you don't. There is nothing more in the kernel. Because if there were, if the kernel was larger than n, then this wouldn't be injective. This would have a kernel, some non-trivial kernel. Any questions so far? Okay, so more concretely, suppose we have a pair of factorization. One is this Fm1, so it's before till F1, and another is, let's say, F prime, M prime, prime, S1. Is a class, this, the dot, 1 prime, two, well, possibly different factorizations. F, pass well, of F, of a class of F, which is an element of phi1 of X. And we want to show that necessarily these two kind of formal products, two words, they are necessarily related by this equivalence relations that we defined of factorizations. Again, one of the equivalents is just the same as in the kind of this reduction which you do in the definition of the free product, and the other is kind of you can treat this element if there is some part of your factorization as an element represented by a path which lives in this intersection, you can treat it as either element of pi1 of one of these sets or pi1 in the other sets. By definition, if these are two factorizations, this means that they are both, so this means that both this thing is homotopic to F and this thing. Position of primed Fs is also homotopic to F, but this means by transitivity, this is there should be path homotopic. There should be path homotopy between these two compositions of paths. And let's denote this path homotopy F, capital F. So this is a map. So as usual, this is a map from square to our X. I remind you is covered by alphas. It's a map such that on one side it restricts to this composition, on the other side of the square it restricts to the other composition. So here we have prime the dot, 1 prime. Here we have position of M dot F1, and here, well, as usual, all these two sides, they will just map to X0. And now we will use the kind of our usual trick that we use the fact that this is, I'm not going to explain details, but so we use the fact that this function is a continuous function, and this is square is a compact, so we can split it into. So again, it's like for each the argument holds like for each point here, you can choose a small neighborhood so that the image of this neighborhood is contained completely in one of these alphas. You can do this for any point. This gives you an open cover of the square, and since it's a compact, then from open cover you can choose a finite subcover. And moreover, since this has a product topology, you can always choose this finite subcover such that by choosing a sufficiently small squares, And moreover, by kind of making them small enough, you can ensure that each of these in this kind of subdivision, each of the closed rectangles is mapped entirely. So f of each of these small rectangles it belongs entirely. The image of each of these small rectangles belongs entirely to one of the alphas. Yeah, the key words here is compactness and continuity. Okay, so we have more concretely. Yeah, let me write okay, let me do the following. So again, the usual argument tells us that we can find subdivision S, this is T, so that you can find a subdivision of each intervals 0, 1, and 0, 1 here. This gives so that you get a subdivision into rectangles of the whole square again, so that each we can require that each closed small rectangle is mapped entirely to one of the alpha. And we want so this is will be a bit hard to work on. We want to modify this a little bit. So instead of this kind of the usual nice rectangular subdivision, we can always say that we can consider a small perturbation of each vertex. Such that we want to make small perturbation each vertex such that in a new subdivision, each vertex, by vertex, I mean here vertex in this vertices in this grid, which you obtain, such that in a new subdivision, each vertex meets at most 3 edges. How can we do this? We can do, for example, we keep everything below this line, but then here you do a small kind of shift each edge here by epsilon. So you keep here in the first row here, everything as it was. So you keep all lines, for example. Also, you keep all horizontal lines as they were, but you make a small shifts of the vertical lines in each other row. For example, here you don't do anything, here you shift a bit by epsilon, here you don't do anything, here you shift by epsilon, here you don't do anything, and so on. And as a result, here you will have each vertex will meet at most 3 edges in this new subdivision of our square by small triangles. Sorry, by small rectangles. And after that, we will finally get the picture which we will actually work with. So we will work with the following picture. look something like this. An example. And we will denote the small rectangles by just Ri. And we will order them starting from bottom from bottom left corner, and we order first them along the horizontal direction, starting from left to right, and then then once we reach the end of one line, we'll go to the second line. So for example, in this example, it will be R1, R2, R3, R4, R5, R6, R7, R8, and so on. And let our final will be something like Rn for big N, for some N. And again, we so the conclusion up to this point. So what we achieved, we choose a subdivision of our unit square such that of the following form, such that each Ri is mapped under our F, so capital F. So capital F with the homotopy map, which is a map from this square to X. The image of each of these small rectangles is contained in some particular A alpha I. Again, so as a reminder, all these two boundary vertical edges, the image is just a single point x0. And if you consider, for example, now we want to what we want to do. We want to consider some paths. Let gamma r, where r will run from 0 to our capital N, and capital N is a total number of the small rectangles in our unit square. So gamma r will be a path square which separates rectangles R1, R2 till R from the rest. I mean, for example, if you write something like gamma, let's say gamma 6, path which separates R1, the collection R1, R2, R3 till R6 from the rest, so you draw it like this, gamma 6. And of course, we orient it so it goes from this H to this H. And so in particular, the bottom H will be gamma 0, and the top H is where our path gamma n will be. So it follows from this construction that if we consider the composition of this gamma r, or gamma r can be understood as the path, and can be understood a map from the interval to the square, and f gives a map from the square to x. Write it. Oh, sure. Gamma r grammatically I can write like this. Gamma r goes to the square, and f takes the square to x, so I can compose them, and the composition will give me a path in x. And more it will be a loop, so this will be a loop x based 0, right? Because since this is because for gamma r, the initial point lies on this edge of the square, and the terminal point lies on the other edge, on the other vertical edge. But we know that the vertical edges, they mapped under f, they map to the same point x0. So this composition, for this composition, the terminal and the initial point, they will be the same, and will be the same as x0. Any questions so far about this construction of subdivision and the passes following the edges of subdivision? And our idea is to do some reduction by this R. So start with this path gamma 0 and do it in kind of small step, increasing the index. Here, go from gamma 0 to gamma n. And we know that here on this on the bottom edge, this capital F was giving us one factorization, and the top edge, the capital F was giving us the other factorization. Then we can show by induction that induction respect this R, these factorizations are related by equivalence, by this equivalence relation that we define. Okay, so how do we do this? So now we use the fact that by our construction, each vertex V in our factorization, so sorry, in our subdivision, square is adjacent to at most 3 rectangles let's say RI1, RI2, and RI3. So you see each vertex the adjacent to it most three rectangles. It can be these boundary vertices, they can be adjacent to just two. And for each, again, by construction, for each of these Ri, its image under capital F belongs to some particular A alpha. And since we know that any triple intersection of A alphas is path connected, in particular the triple corresponding to these three small rectangles is path connected. And then it follows there exists a path GV, so it's a path for our chosen vertex V. Which is with the image being in this triple intersection. Again, is a subset in X. Pass from X0 to F of B. B is a point in our square, and under F, it mapped to F of V. And this is definite by construction. This is, of course, a point also in triple intersection, right? Because it belongs to all, this point belongs to all three rectangles here, and therefore F of it belongs to all three alphas. And so using these passes GV, we can construct factorization of this composition of F and gamma R for each R. For each R from 0 to n, there is a factorization position given by the following following product. So how exactly we construct the fixation? First of all, of course, since so how does this gamma looks like? Gamma R. So it's so I draw kind of a relevant part of this square which we have before. So it's some gamma pass kind of form which pass inside this unit square, and along the path we can encounter this path gamma R. Along the path we can encounter some vertices, for example V1, 2, V3, V4, V5, and so on. So we can choose them to label such that they order it. So on. And for each of these small intervals along gamma R contained between two vertices, we can consider this interval to be a part of this gamma R, denoted by correspondingly the first interval will be gamma R1, the second interval will be gamma R2, meaning there is a small path going along this interval, gamma R3, and so on. Well, by construction, gamma R is a composition of one, gamma 2, dot, and we have the corresponding composition gamma R. This gives this composition of this of the composition of functions here. So we can write correspondingly here, or we start then. It will be f composed with gamma R1, followed by f composed with 2, on. And then we can do again as a kind of our usual trick. We can insert composition of paths and the inverses. So here, in particular, we can insert V1 bar, then followed by GV1 is the same, then followed by, so GV1 is a path going from f of V1. GV1 bar is a path which goes from f of V1 to x0, and GV1 takes you back from x0 to f of V1. Then you can follow along composition of f gamma R2. Then you insert GV2 bar, 2, and so on. You can see this now is a loop X based 0. This is also loop in X based at X0, and so on. This gives you a factorization of this composition in terms of loops in X based at X0. But moreover, you can notice that, so suppose, consider some particular element here. So we have an element of the form G. Generically, we have an element of the form GVI bar times F gamma I R I minus 1. This is what you have at i's place in this composition. And so you can see that, so this is somewhere, this is what happens, again, somewhere here. So you have a small piece of gamma, which is gamma R I. The piece contained from, which is going from the vertex V I minus 1 to the vertex vi. And here what happens is that, okay, you can, so below and, so this if you consider this edge in our subdivision, it separates two rectangles. Suppose RA and RB. And so if you consider okay, you can consider this edge both. So this edge both belongs to RA and both to RB. And since if you consider this edge as the edge of RA, you can argue that so the homotopy class, you can say that homotopy class of this loop belongs to pi1 of A alpha A, right? Because by construction, this is contained in A alpha A, since this H is contained in RR, and we chose our passes G, so the path G, it belongs to A alpha for each rectangle in which it's contained. So all of these three guys, they contained in A alpha A, so it represents an element in this fundamental group. But you can also equivalently consider this H as an edge belonging to RB. And then you would consider this as an element of pi1 of alpha B. So there seems to be some ambiguity, so we can define, again, this defines a certain factorization, but each of these factors can be assumed as an element of pi1 of this guy or pi1 of another guy. Well, this is actually what we expect. There's actually nothing wrong here. One can notice that this ambiguity results two equivalent factorizations. So this is this was a second part of our equivalence relation. You can treat if some path in factorization belongs to kind of simultaneously to a pair of sets in our cover, you can equivalently treat it as an element of pi1 of one of them or pi1 of the other. Second, we can notice that factorizations responding to gamma R plus are equivalent. So why is that? Suppose let us draw it here. We have some path gamma r now square, and let's consider a path gamma r plus 1. So they kind of differ by the small square r with index r plus 1. R 1 here, and this is gamma. Jump by 1 square when you change gamma r to gamma r plus 1. And this means that so obviously you can, if you consider this as a path in this square which we have here, you can homotop gamma r and gamma r plus. And you can always choose a homotopy, just for example, linear homotopy, so that at any value of the homotopy parameter, this part stays entirely in this small rectangle, capital R with index r plus 1. So you can say that gamma r plus 1 and gamma r are related by homotopy square, meaning you fix some particular, so again, you consider sort of factorization of this decomposition in some composition, consider this gamma as a certain composition where you fix parts of them outside of the square and separately parts which is belongs to the square. And then you do just homotopy on these parts, and you keep this homotopy inside this small rectangle. Therefore, the respective compositions, namely with capital F takes us from this square to space X. Corresponding compositions are related by homotopy F of R with index R plus 1, which is by construction contained alpha, A alpha with index R plus 1. And this essentially tells us that if we in up to this, so we can always make this choice, which we had here, so that these parts of gamma are considered as belonging to this given rectangle, and then this homotopy results in these elements which appear in factorization, namely the equivalence classes to be just the same. So we checked this statement. factorization corresponding to gamma r and gamma r plus 1 are equivalent. Actually, okay, I shouldn't have erased this picture, but okay, let me show it here. So we start. So what we showed essentially, okay, so there is some square, and as we already argued, the bottom. So we can start at the bottom with gamma 0, and we can follow at top. We'll have gamma capital N, and so far what we showed that if you go this kind of if we change this index by 1, we result in equivalent factorization. So now we just need to show that indeed for gamma 0 and for gamma n we have we indeed get the factorizations which we started with. Remind you, we started with a pair of factorizations, arbitrary factorizations, and we want to show that they are necessarily equivalent. And okay, this can be done by making the following observation. We can assume mind you, so here, so this we have consider coordinates S and T in our square, where S is a parameter for path and T is a homotopy parameter. Have some vision. We can assume that S partitions, meaning that how we divide S partition, meaning the partition of the horizontal interval somewhere here at equals 0 and 1, meaning the partitions here and here of the horizontal intervals. These partitions subdivide partitions are used factorizations. That we started with. So there was factorization. M of m minus 1, dot f1.
Camera is not moving.
Sorry, what was that question?
We can't see what you're writing.
Oh, that's strange. Well, I guess I can, okay, you see this part, I can start here. So what I was saying is that we have some subdivision of the square on rectangles, and we can assume that S partitions equals 0 and equals 1 meaning the partitions of the horizontal intervals at top and the bottom of the square, subdivide partitions we have for factorizations that we started with. Pair factorizations. This, the other is primes, meaning the following. So we have at the bottom, we have this gamma 0. Zoom in and see the part of this gamma of the gamma 0, which lies along the bottom edge of the square. So we have again by our construction the restriction of the capital F at the bottom edge should be correspond to our factorization like this: fm minus 1 till f1. So in particular, there will be some part of this bottom edge for which the restriction of capital F is fj for some j appearing here. And so we can always assume this our subdivision, which used to be such, without laws of generality, to be such that the edges kind of one of the vertices, these boundaries of this interval, which correspond to a particular factor fj, coincide with some of the vertices in our subdivision. So here, somewhere in between, we have I, the I plus 1. Respectively, this will be some Rj, Rj plus 1. Two rectangles. And by construction of the factorization, we know that the image of fj, so this part of the path f, which corresponds to this interval, belongs to one of the A alphas. Well, let me call it beta, for some beta. And we can also consider the pair of A alphas corresponding to a pair of consequent rectangles here. So A alpha j and A alpha j plus 1. And we consider the intersection together with the intersection of this A beta. Again, we know that for any triple, the intersection is path connected. And so there exists a path. Particularly, there exists a path G I, which belongs triple intersection. So what we before, how we constructed the passes. So for each vertex, I remind you, for each vertex in our subdivision, we constructed a pass which whose image was contained in the intersection of A alphas corresponding to the particular small rectangles. Okay, so for this guy, there was just two rectangles which it belongs to. And
Sir,
yes.
Doesn't GVI start at X naught?
Well, it starts, so what we had, how we defined GV was a pass from X naught to F of V, right? And we chose it so that, okay, for general vertex, there are three surrounding rectangles, right? And for each of them, for each of these rectangles, there are corresponding element, well, let me call A, B, C, right? And we chose it, the GV, the image of GV is in A alpha A intersection of A alpha B.
Professor, again, the camera is stuck somewhere else.
Okay. Well, I guess you can see this part. Yeah, how we chose GV. So there was some vertex V, and there was a, so suppose if this is it was an internal vertex, then there were three small rectangles to which it belonged. And we chose GV was as a pass from X0 to F of V, which is side this triple intersection of open sets corresponding to this triple, right? And okay, if there now if you have a vertex on the boundary, so for example, as here at the bottom edge, we don't have any this third guy. But you can make an addition. We can, instead of considering this RC, we consider now and the corresponding A alpha C. What we do, we consider A beta, where beta, this A beta is a open set where this pass Fj lives. And then instead of this triple like this, we consider triple here. And we can again require, by considering this triple, we can require this G corresponding to this vertex here to be, again, a pass from X0 to FV, but now contained in this triple intersection. Is it clear, or is there still a question?
Okay, Professor.
I guess I have to continue using just this part of the board, just in case. So I have to erase. Finally, okay, so we're almost done. So from this observation, we know that factorization, we observe that the factorization make this choice of the GVs corresponding to boundary vertices V, factorization corresponding to gamma 0 is equivalent. Our first factorization. Because each of these guys is just gives us a just a product of these factors which we constructed, which we define for general gamma R, and similarly, so we consider a bottom edge, but similarly we can consider top edge factorization corresponding to gamma R is equivalent to second. Since we showed, sorry, gamma n, the final. Since we showed that if we increase this index of gamma by 1, we change factorization by equivalent 1. This means that these two these two factorizations are indeed equivalent. So collecting these points from 1 to 4, we get that indeed this double star and this triple star is indeed equivalent. This is what we wanted to show. So this is finally this is finishes the proof of the theorem, and in the next lecture I will consider some examples of the how we actually use. So the proof may be complicated, but what will be important, in particular for homework and for exam, is actually how to use this statement. And the corresponding examples we will consider next time. Are there any questions? If not, that's it for today.
Thank you, Professor.